Now, let's formulate a simple problem in the throwing of two dice. Two dice are thrown. Now, we are told that the sum of the face values of the two dice is 8. What now is the chance that at least one of the two dice shows an ace? Now, this perhaps is not quite so intuitive, and maybe it's not so easy now to arise or jump at quickly at the wrong answer. But if you like, pause for a moment and think about it and see if you have an instinctive feel, an intuitive feel for what the answer might be. Start the lecture again when you're ready. Now, absent any immediate intuition for the problem, we should start again by constructing a probability space for it, and we should begin with a sample space. Now, we have seen this sample space before in Tableau 3, Part 3, when we talked about the dice game of craps. Now, in this setting, the sample space is naturally obtained by identifying the results for each die in turn, say die 1 and die 2. The sample space then becomes a system of ordered pairs of integers where the elements run from 1 through 6, the possible faces for the die. The sample space has got 36 possible outcomes. 6 possibilities for the first die, 6 possibilities for the second die. In this space, what are the subsets that give rise to the events of interest? Again, let's color code these subsets. Let A denote the event of interest, which is that at least one of the two dice shows an ace. We think about this for a moment. We can identify precisely those pairs for which one of the two elements, I and j, shows 6. And we can enumerate them very systematically. For example, the first die shows a 6, and then the second die can show any of the numbers from 1 through 6. Now, or the second die shows a 6, and now the first die can show any of the numbers from 1 through 5. And there are now 11 possibilities in total, and these comprise the event A. What about the side information that we are told about the outcome of the experiment? Well, we are told that the sum of the face values is 8. Notice we're not told what the outcome is. We're not told what each of the two dice is showing. What we are told is that this, whatever the outcome is, it falls into this category. This is the information we have. Now, the sum of the two face values being 8 will constrain the possible pairs to 5 in number. 6 and 2, 5 and 3, 4 and 4, 3 and 5, or 2 and 6. There are exactly 5 possibilities and no more. Now, the two events at hand are clear. We now need a probability measure. And again, the natural probability measure here is combinatorial. We have a discrete setting, a finite setting with 36 possible outcomes. And naturally enough, we assign an equal atomic probability of 1 in 36 to each of these 36 possibilities. Even probabilities are, by an appeal to additivity, obtained by simply adding up the atomic probabilities in each of these events. Since A has got 11 sample points in it, the chance of A is now 11 in 36. And since B has got 5 sample points in it, the chance of B is now 5 in 36. Again, a visual picture might drive this abstraction home. We can depict the sample space in a 6 by 6 array of numbers. This is omega. There are 36 elements. Each square here represents one possible outcome. The event A of interest to us, where there's at least one 6, is obtained as the band around the edge in red shown in the figure. The chance of A then is, naturally enough, 11 out of 36. This is the unvarnished chance that you get at least one ace when you're told nothing else about the outcome of the experiment. But wait, we're told something about the nature of the outcome. we are told that the sum of the face values is 8. The event B is obtained as those 5 squares along a diagonal in your figure. Once you're told that B occurs, none of the other elements could have occurred. We have expunged from the 36 possibilities 31 possibilities. The sample space has now been reduced effectively to just B alone. And in this new sample space, we have 5 possibilities, and of these possibilities, precisely 2 trigger A. The possibility the first die shows 6 and the second die shows 2, and the possibility that the first die shows 2 and the second die shows 6, again highlighted with red borders in your figure. Now, once you're told that B has occurred, this is the entirety of a new sample space. To normalize it properly, we have to ask ourselves, now, not as what is the chance of A among the universe of original possibilities, but what is the chance of A among the reduced possibilities that constitute B? The chance of A now, given that B occurs, and therefore we come to the conclusion that given that the sum of face values is 8, the chance of observing an ace, at least one ace, on the 2 faces must inevitably be 2 in 5. These simple chance experiments in very commonplace settings already allow us to identify the key elements of how we wish to fold side information formally into the abstraction process. For our purposes now, side information is always provided, when it is present, in the form of an ancillary event. The moment we specify an ancillary event, the question then is, how does the target event, in this case A, interact with the ancillary event B? Ineluctably, they are twinned together, and in this twining arises a conditioning of factoring in the side information. So this is the basis of the formal definition that will arise next.